So, we are looking at method of characteristics approach to solve supersonic flow field problems in case of inviscid rotational isentropic flows. Okay. So, and in the previous classes we discussed what these characteristic lines are and how do you get the characteristic equations and compatibility conditions for a 2D supersonic flow. The characteristic lines are C minus and C plus. The slopes of the characteristic lines dy by dx is tan of minus mu, where mu is the Mach angle for C minus characteristic, and tan of theta plus mu for C plus characteristic. Along the characteristic lines, theta minus mu, that is the Prandtl-Meyer angle, theta for the C minus it is theta plus mu, that is constant. For C plus it is theta minus mu. So, these are given values k minus and k plus, these are constant. And we also had an introduction to what is meant by contoured nozzle, where the nozzle is designed in such a way that the flow at the exit, right, the flow at the exit is uniform. Otherwise, if the nozzle wall is not properly contoured, then these characteristics keep reflecting off the walls, and at the end you get a non-uniform flow. In order to get a uniform flow, you have to design the wall in such a way that it cancels the waves, these Mach waves, once they impinge on the wall. That can be done by making the wall angle equal to the flow angle at each Mach wave. Okay. So, that is what is the principle that we are going to use and to look at how to design such nozzles. Okay. We had a relationship for what should be the flow turn. So, now I know what should be my exit Mach number, ME is known. I have to give a certain flow turn, so that the flow expands here, that is the theta wall maximum, that is the theta wall that I have to give in order to achieve a certain Mach exit, and this relationship was theta wall max is equal to Prandtl-Meyer angle of the exit flow divided by 2. Okay. This also we proved by using method of characteristics itself. So, now let us apply this process for design of a minimum length nozzle for Mach 2. We will just consider 2 points, because you can see just for these 2 points we have 1, 2, 3, 4, 5 points need to be evaluated. Also properties at 1 at 0, which is the originating point. We have uniform Mach 1 flow at section 0. Sometimes this is not always true. You may have certain non-uniform flow also may be present, but the flow is supersonic. If the flow is supersonic, then that can be considered, and you can draw a initial characteristic net starting at this particular point. So, that there are methods, detailed methods for that on how to consider such situations, which is not in the scope of what we are discussing. We are just discussing that we have an uniform flow, and then we turn it by a Prandtl-Meyer expansion at as a corner over here, and then look at designing a wall such that there will be no wave reflections at the wall. Therefore, at the end you will get a uniform flow. If this needs to be achieved correctly and a smooth profile needs to be got, then we need a large number of waves. You may need to take hundreds of waves in order to get a smooth profile. But here for a classroom case, we will just take 2 characteristics. We will see the procedure so that you become familiar with it, and if somebody is applying this in their work, then they need to actually write a MOC code, a simple code in order to do this calculation for many waves. Okay, so let us begin from we look at the point 0. So at the point 0 you can see, so this is the point 0, and here this flow here is uniform Mach number equal to 1, and the flow turns at point 0 by an angle. So Mach number equal to 1, theta equal to 0, and it turns by an angle theta wall max, which is equal to nu by 2, Mach exit by 2. Now this total turn can be accomplished by several set of waves. In this case we are considering only 2 waves, one the final flow turn and the one at a half of that. So the flow turn for say Mach number 2, the theta wall maximum needed to be achieved is 13.19 degrees, and that is divided into 2 angles, one at 6.595 and the other one at 13.19. Corresponding Prandtl-Meyer functions are also 6.595 and 13.19. You are using the Prandtl-Meyer relations here, and delta theta is nu 2 minus nu 1, but Mach number is 1, so nu 1 is 0. Therefore nu 2 is equal to delta theta, or in this case since theta is also 0 initially, nu 2 equal to theta 2, or basically nu 2 is theta. So the points, there are 2 waves essentially. They are we are considering that the half angle or the half height of the nozzle at the throat is 1. So you can appropriately scale these coordinates once you get the results. Now when we do this kind of solution, we are solving both for x and y as well as the flow properties at each point. It becomes very difficult to keep track of these various quantities. Therefore it is useful to always have a table of this sort when you are doing it by hand. Otherwise generally people write a code to do this automatically. To understand the procedure we can do for a few points, so that this procedure becomes one can use this procedure. So at the wave which is 1, we know theta value, we know nu value, corresponding Mach number is 1.315 and corresponding mu, that is Mach angle is 49.48. The value of k plus and k minus is also given here. K plus is theta minus nu, that is 0, but k minus is theta plus nu, which is 13.19 and 26.38 for the 2 different waves. Now we go to point 1. Now point 1 is located here. It is the first wave that is produced at point 0. It is going and coming to the point of line of symmetry at point 1. So we apply the symmetry boundary condition here, that is theta 1 is 0. This is a C minus characteristic. So theta 1 plus nu 1 is equal to 13.19. it is already known, but theta 1 is 0, therefore nu 1 is 13.19. Therefore corresponding Mach number you can get is 1.543, and corresponding the Mach angle also you can get 40.38. Now how to get the value of x and y here? Here this is the x y, so this is along x coordinate, this is y coordinate. Now this is a point on line of symmetry which is at x axis, so y is 0, but we need to find the value of x. For that you write the equation for this particular C minus characteristic, which is y2 minus y1 by x2 minus x1 is equal to, or in this case it is y1 minus y0 by x1 minus x0 is equal to tan of the average angles, essentially the average angles. over here, average of 6.595 plus 0 by 2, 49.48 plus 40.38 by 2. This the coefficient here is this value, and you can get x 1. So, now we got x 1 here. So, we write the value for 1 here, x is known, y is 0, theta is 0. Now, we knew we got it is 13.19, corresponding Mach number and mu are also written, and the value for the value of the slope that we used. So, that we got the values for x and y is also given over here. Now, k plus and k minus can be determined again here. K plus now is theta minus mu, which is minus 13.19, because theta is 0 and mu is 13.19. Okay. So, now we go from point 1 to point 2. Now, point 2 is an interior point. So, this particular problem is also an description of various unit processes that we had discussed. So, at point 2 we have a C plus characteristic coming from 1 and a C minus characteristic coming from 0. This is the second wave from 0, and we know for C, that is, this is the value for k plus coming from 1, and this is the value for k minus coming from 0, that is the second wave from 0. So, we know these values. So, just we have to solve them algebraically. You have the equation for that. From here we can calculate what is theta 2 and nu 2, which is the Prandtl-Meyer angle. So, theta 2 is 6.595. So, you find that this flow is not uniform, because here the angle is 0, theta is 0, but here at point 2 it has an angle 6.595. So, the flow is deflected by 6.595 degrees with respect to x axis. Mach number has increased, it has come to 1.7675, and similarly mu 2 has changed. Now, we need to find x 2 and y 2. We write the equations of straight lines between these 2 points. So, 0 2 and 1 2. We know the values for 1, that is already known, and we know the value for 0. We substitute those values and we get the numbers now, x 2 and y 2. Okay. So, now this can be again put into the table. So, we can keep expanding the table. Now, point 2 is available. So, it is slightly downstream of point 1 and slightly above the line of symmetry, and here the flow is having an angle of 6.595 degrees. Okay. So, now we look at the first wall angle. If you follow this particular characteristic, C plus characteristic, after point 2 it goes to the wall point. Now, in order to ensure that there is no wall cancellation, the angle at the wall should be equal to the angle of the flow. The angle of flow at this particular point is 6.595. So, the wall should match that. So, you get theta wall equal to theta 2 equal to 6.595. The slope here is 6.595 degrees. Okay. So, now we know the wall angle at 0. This wall angle is theta w max. This is known to us. Now, we know the wall angle at this particular point, okay, that is 6.595. So, this equation is also estimated to be a straight line. So, in this case these 2 points are far apart. So, we will get a small error here, that is understood, but when this is really done, it is done in computers and several waves are used, very large number, say hundreds of waves are used. Then the points are very close to each other, and therefore you can actually get a smooth profile. But for classwork sake or classroom sake, we will just take simply a fewer number of points, and therefore you just write the equation of the straight line between 0 and W1 and 2 and W1. We take average angles again, and therefore we get these two equations, and the previous values are substituted here, and in the locations for points of 2 and 0, and we can get the values of wall as xw1 and yw1. Okay, so you are getting these numbers now. So this number is away, much away. So this is about 1.4967, and the location is 2.8482. So now we can continue this approach, go to point 3, that is a symmetry point. Now this point is coming from the second wave after it has passed through point 2. So we have to take the C minus characteristic from point 2 and let it come to point 3, and here at point 3 you will find that the value of Mach number at 3 will be equal to 2 and the angle is 0. This is exactly what is required, and consequence the wall angle at W2 should also be 0. Okay, so that should be the case. So that should be the end of the wave cancellation section, and you write the equation of C minus characteristic again, and here y is 0. So you can solve for this starting from the point 2, and you get x3 is 1.891. Okay, so you got value of these different numbers now. Now you can further go to wall point 2. At wall point 2, the value of theta is 0, so it is the end. So it has become parallel to the x axis. So you get a uniform flow here. Mach number is 2, Mach number is 2.0, and you can get the x and y values by considering the previous wall point and a straight line from there, and a straight line from theta 3 and the intersection of those two, and here you get y wall is 1.602. Okay, so if you if we had looked at the area ratio for Mach number equal to 2, we will find that y should be from isentropic area ratio relations, it should be 1.6875. Of course we have considered only very few waves here. If we take a good number of waves, we will get a more accurate solution, but even considering 2 waves, we have got a solution which is very close to the expected values. Okay, so now by this set, so now we have completed all the different things, and we have got the points W1 and W2. If you take many number of waves, we can get a smooth contour. So for people who are going to use this, they need to develop a small code to compute for large number of waves for their particular problem. So I hope with this example you get an idea of how to use MOC for solving supersonic flow fields. It can be used for analyzing supersonic flow fields, or it can be used for designing supersonic nozzles. This is a particular case where we are looking at analyzing a flow field, understanding how a flow field looks like by knowing the initial values. This is the case of analyzing a supersonic free jet, that is the jet a jet from, like, it can be a contoured nozzle, it is coming out into ambient, and the initial conditions of the jet are given. P naught is given 6 bar, T naught is given 300 Kelvin, and Mach number is 2.0, So, if you calculate this at this particular exit location, what would be the pressure corresponding to Mach number 2.0, it can be shown that this pressure is actually less than 1 bar. That means this nozzle is in the working in the over expanded condition. As a consequence, it will develop oblique shock waves. Now, this oblique shock wave will come to the center line. At center line, of course, the flow has to maintain theta equal to 0 condition. So, in order to ensure that that happens, because if you consider a streamline here, this streamline is deflected towards the flow, but at this particular region the flow has to be parallel again to x axis. Therefore, another shock develops. As a consequence of two shocks, you get region 3 which has much higher pressure. Okay, so, if you look at the centerline pressure variation, initially you have a pressure which is lower than ambient pressure, and then suddenly the pressure will increase higher than ambient pressure. In the region 2, it will be exactly ambient pressure. This is a case where we are looking at a reflection of waves from a free pressure boundary, and we know for to achieve that always the pressure at the boundary should be 1, and we find that pressure at 3 is higher. As a consequence, it develops expansion fans, and then further you can see how pressure varies. Here flow is non-uniform and pressure varies in a smooth manner. So, this analysis can be carried out using a method of characteristics and shock waves together. In regions in those shock waves are discontinuities. So, across the shock wave there is a entropy jump, but once you get into uniform regions they are isentropic. So, those regions can be still analyzed using MOC. At the shock you will have to apply the shock jump conditions. So, if you look at that, so at in region 1 if you find out what is the pressure by looking at nozzle P0 by P for Mach 2, you find pressure is 0.7668 bar. Now, region 2 has pressure equal to P ambient equal to 1 bar. Okay. So, we know the value of P2 by P1 across the shock. Okay, this value is known. Since we know the pressure ratio across the shock, we know that that for an oblique shock it is dependent only on the normal Mach number upstream of the shock. So, we can get Mn1 which is 1.1228. If you know the Mach number, M1 is known and Mn1 is known, we know Mn1 is equal to M1 sin beta. Therefore, you can get beta. Now, M and beta is known, we can get theta also. So, we get how much the flow is deflected. It is deflected by 4.824 degrees. Pressure in this region is 1 bar, but in order to make sure that the flow remains parallel in at the line of symmetry, this shock wave develops between region 2 and 3. So, Mach number in region 2 is 1.827. Okay, this is just by oblique shock equations, you can solve for it. Now, it is a symmetric flow. So, between 2 and 3 another shock forms, again you can calculate it, you know Mach number in M2, then you know what the flow deflection should be, it is the same 4.84 degrees. Therefore, you can know M and theta is known, you can find out all the other parameters, what is P3 by P2 and so on. So, here pressure becomes 1.287 bar. Okay. So, now pressure has increased in 0.3, but again you require in this particular region a constant pressure of 1 bar. So, across these 2 points, regions between 3 and the region that is represented over here, we will have an expansion fan, and that expansion fan can be solved using Prandtl-Meyer's theory. Okay. Here Prandtl-Meyer's expansion is an isentropic expansion. and we need to find what is stagnation pressure in region 3 P03. This can be found, it is 5.982 bar because of two shock waves. You see that the stagnation pressure has reduced from 6 bar, this is due to entropy generation in shock waves. Okay. Now this pressure is higher than ambient, so you will get an expansion. You know the pressure over here which is 1 bar, therefore you know pressure across the Prandtl-Meyer expansion fan, and therefore since the flow is isentropic we can calculate what should be the Mach number of the final wave, okay, after which it again gets into uniform flow, and that Mach number is found out. Okay, so that Mach number is 1.83 and corresponding flow deflection can be found, it is 4.85 degrees. So now this Prandtl-Meyer expansion, now if you see this region, it is very much similar like the analysis of the supersonic nozzle that we just conducted right now. So we will not go into all the details here, but just understand how we can get the pressures at these points 4 and 5. The initial line, so the head of the expansion fan is here and head is here and tail is here. So these are Mach waves at those particular values. So we can consider two different set of waves, again similar to the way we did for supersonic nozzle. We divide the total turn into 2 turns. Okay. So use these are C minus characteristics. So you have theta plus nu is constant, and at the point 4 it is a line of symmetry, point 4 and 5. Therefore you get the value of Mach number at 4 and 5 because theta is 0. If you know the value of nu phi, you get m5. If you know m5, we can calculate p5. So by this way we can continuously find out this, and this in turn continues as a whole cycle. In fact, if you take a picture of these supersonic jets, you find these shock cells and expansion cells and shock waves and expansion waves, they continue for a very long duration. So this is just the initial part of it we have analyzed in greater detail than what we were doing using one dimensional theories. So similar analysis can be carried out for under expanded jets as well. Okay, so that can be done, is a very similar process can be carried out. Now once the expansion waves reflects off the constant pressure boundary, we know they become compression waves and ultimately can coalesce to form a shock wave, which is what happens over here. Okay. So we saw now that method of characteristics is a very useful technique, not only to look at the design of contoured supersonic nozzles, but to solve supersonic flows in general. If you can find regions where flow is isentropic and it is also non-uniform in general, still that can be solved using method of characteristic, provided you know some initial conditions and you can march from that initial condition into the flow field and solve the entire flow field. Here unlike what currently we do in many cases of CFD, where we have a given mesh and we try to solve the equations over the mesh, here both the equations and the solutions are done simultaneously. So you solve the characteristic net as well as you solve the flow properties at every section as you move in forward direction. Okay. With this we come to a close of discussions on the flow field kind of analysis in subsonic supersonic flows. We saw two kinds of approaches. One was the small perturbation theory, and in supersonic flow we saw method of characteristics, a useful approach again. And this covers majority of the contents that we had planned for this particular course. The intention also here is that to introduce you to several special topics in that we find in compressible flows. Very many interesting facts or very interesting flow features are present, but it is not possible to cover all of them in a short course. They are full courses in themselves, but a brief idea can be presented of specific topics like what do you mean by hypersonic flow, or how does flow look like in real cases where there is viscous effects along the walls which forms boundary layers, and there are also shock waves in supersonic flows. How do they interact with each other? And we have talked about reflection of shock waves, but often we sometimes find, for example, even in the jet problem, that two shock waves interact with each other. Those are shock interactions, and these are very much present in all practical applications of compressible flows. So we will just introduce these topics towards the end of this course in the subsequent classes, so that people interested in them can take them and learn more from other references. With that, we close this class. Thank you.